Welcome to Sleepy Science. Tonight, we're not just looking at the stars. We're traveling back to the very beginning of everything. Before the galaxies, before time, before even space itself. There was a moment, a spark, a breath that gave rise to everything you know. This is the story of how the universe began, told not with chaos, but with calm, as we trace the quiet rhythm of creation. For as long as humans have looked at the sky, we've asked the same question. Where did it all come from? Ancient cultures built myths and stories to explain the heavens. They imagined gods throwing fire across the void, or cosmic eggs hatching stars. But modern science offers a story no less wondrous. A story written in light, gravity, and time itself. Today, that story begins with a theory called the Big Bang. The idea that the universe started from an incredibly hot, dense point about 13.8 billion years ago and has been expanding ever since. The name Big Bang can sound like an explosion, but it wasn't one. There was no sound, no blast into empty space, because there was no space yet. The Big Bang was the sudden appearance and rapid stretching of space itself, carrying energy and matter outward. To understand it, imagine not a bomb going off, but a balloon inflating. Every point on its surface moves away from every other point as it expands. There's no center, no edge, just growth, calm, smooth, and unstoppable. That's how the universe began to unfold, from something smaller than an atom to the vast cosmic web we see today. At the earliest moment, a time we call the Planck epoch, less than 1/trillionth of a second after the beginning. All the fundamental forces of nature were one: gravity, electromagnetism, and the nuclear forces had not yet separated. Temperatures reached 1032 degrees Kelvin, far beyond anything that can exist now. Matter as we know it couldn't survive. Only pure energy filled the tiny, curved space. We cannot yet see into that first instant. Physics, as we know it, breaks down there. The equations stop working. But just after that incomprehensible beginning, something extraordinary happened. The universe began to cool. As it expanded, energy condensed into the first particles. Quarks, electrons, neutrinos. The seeds of everything that would ever exist. Within fractions of a second, the four fundamental forces separated, each taking its role. Gravity began to shape the structure of the cosmos. The strong nuclear force bound quarks together to form protons and neutrons. The weak force allowed certain particles to decay, and electromagnetism began to control how light and matter would interact. The rules of reality had been written. Though the universe was still smaller than a grain of sand, it contained all the energy and potential for galaxies, stars, and life. The darkness we see in the sky today traces its origins to that moment when existence itself turned from pure energy into the building blocks of matter. As the expansion continued, something else began. A brief but unimaginable burst called cosmic inflation. In less than a blink, the universe grew from subatomic size to something billions of times larger. Space itself stretched faster than light, not violating any laws, because the expansion of space is not motion through space. Inflation smoothed everything out, explaining why the universe looks nearly uniform in every direction. When inflation ended, the energy that had driven it transformed into a sea of particles and radiation. The universe glowed, dense, hot, and bright beyond description. From that glow, all creation would eventually emerge. This is how the story begins. Not with sound or fire, but with expansion, cooling, and order slowly taking shape out of unimaginable heat. The beginning of the universe was not violent in spirit. It was a quiet unfolding of possibility. In the next part, we'll move forward through those first seconds, how particles combined, how the first atoms were born, and how light began its long journey through the dark. The beginning has only just begun. After the first instant of creation, the universe began to expand at an astonishing pace. In just a fraction of a second, it grew from something smaller than a proton to something vast enough to contain the seeds of everything that would ever exist. This was the first measurable moment in the story of time, the first second of the universe. During this brief but crucial period, everything that defines our physical reality began to emerge. At first, the universe was unimaginably hot, temperatures near 1 trillion degrees. Matter and energy existed as a single chaotic mixture of fundamental particles: quarks, gluons, electrons, positrons, and neutrinos. Photons, the particles of light, were everywhere, colliding constantly with everything else. At around 10 seconds after the beginning, the universe cooled just enough for quarks to join together. Under the strong nuclear force, they formed protons and neutrons, the building blocks of all atomic nuclei. It was still too hot for atoms to exist, but for the first time, matter began to take form. In the next few seconds, neutrinos, ghostly particles that barely interact with anything, escaped into space, traveling freely through the expanding cosmos. To this day, they still fill the universe, a relic of that first second. By about 1 second after the Big Bang, the universe's temperature had dropped to about 10 billion degrees Kelvin. Still unimaginably hot, but cool enough for the first nuclear reactions to begin. Protons and neutrons began to collide and fuse, forming the lightest elements: hydrogen, helium, and trace amounts of lithium. This process is known as Big Bang nucleosynthesis. For the next 3 minutes, the universe was a vast nuclear furnace. The ratio of protons to neutrons determined how much helium would form, roughly 25% by mass, with the rest remaining hydrogen. That balance, set in those few minutes, still defines the chemical makeup of the visible universe today. After that point, temperatures fell too low for fusion to continue. The universe was full of light, but that light couldn't travel freely yet. It was constantly scattered by electrons, like sunlight bouncing endlessly through fog. The cosmos remained opaque, a glowing, hot plasma of particles and radiation. For hundreds of thousands of years, this dense fog persisted. Gravity began to pull matter into slightly denser regions, but everything was still too energetic for structure to form. The universe was smooth, expanding and cooling, a vast ocean of light and matter waiting for the next stage of transformation. If you could have witnessed that first second, you wouldn't have seen stars or galaxies. Just a blinding glow filling every direction. There was no center, no edge, and no silence, only motion, energy, and the slow unfolding of order from chaos. In that first second, the universe established the physical constants that would govern all things: the speed of light, the strength of gravity, the charge of the electron. Even the tiniest variation in those values could have prevented matter, atoms, or life from ever forming. Everything we see today, every world, every mind, owes its existence to that delicate balance. By the end of the first few minutes, the universe had set its foundation. The building blocks of stars and galaxies were in place, drifting quietly in the hot radiation of the newborn cosmos. The forces were stable, the laws of physics were defined, and time itself had found its rhythm. From that point forward, the universe's story would be one of cooling and structure, of light finding freedom, of gravity shaping clouds into stars, and of energy slowing into matter. The chaos was ending, and the cosmos was beginning to take its first calm, luminous breath. In the next part, we'll explore the age of light and separation, when the universe's glow finally thinned, atoms formed for the first time, and the darkness we now call space was born. For the first few 100,000 years after the Big Bang, the universe was a brilliant storm of light and matter. It glowed with radiation so intense that no atom could exist. Protons and electrons collided constantly, breaking apart any attempt at structure. Space itself was filled with a dense, shining fog, a plasma where light could not move freely. But as the universe expanded, it cooled. The temperature dropped slowly from billions of degrees to a few thousand. When it reached about 3,000 Kelvin, something remarkable happened. The photons, the particles of light, no longer had enough energy to break atoms apart. Protons could finally capture electrons, forming the first stable hydrogen and helium atoms. This event is known as recombination, and it changed everything. For the first time, light was free. Photons that had been bouncing endlessly through the plasma could now travel in straight lines, escaping the fog and filling the universe. That first light still exists today. It has stretched with the expansion of space for 13.8 billion years, cooling into the faint glow we call the cosmic microwave background radiation, a quiet, uniform signal that bathes the entire sky. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, this radiation is one of the most important pieces of evidence for the Big Bang. It is a photograph of the universe when it was only 380,000 years old, showing faint patterns, tiny temperature differences that would later become galaxies, stars, and clusters. Those subtle ripples were the first hints of structure in an otherwise smooth cosmos. The universe at that time was filled mostly with hydrogen, about 75%, and helium, about 25%, along with trace amounts of lithium. There were no stars, no planets, no light beyond the faint background glow. It was a simple universe, governed by the quiet rules of physics, expanding and cooling in every direction. As it continued to expand, the temperature dropped further. The wavelength of the original light stretched from visible colors to infrared, and eventually into the microwave spectrum. Today, this ancient radiation has cooled to just 2.73 Kelvin, barely above absolute zero. Yet it still carries a perfect record of the early universe's conditions. The formation of neutral atoms also allowed gravity to begin shaping the cosmos. Before recombination, the pressure of radiation prevented matter from clumping. But now, with light no longer pushing against it, hydrogen gas could start to gather under its own weight. Slowly, over millions of years, denser regions grew denser still, while emptier regions became more void-like. This was the dawn of the cosmic dark ages, a time before the first stars, when the universe was transparent but unlit. It was not dark in the way we imagine darkness now. It was clear, empty, and silent. The only glow came from the residual radiation of creation, fading steadily as the universe expanded. For the next few 100 million years, the universe remained calm. Gravity worked quietly in the background, pulling gas into invisible clumps. Within those clumps, density increased, temperature rose, and the first stars began to form. The darkness would not last forever. Today, by studying the cosmic microwave background, scientists can measure the universe's age, its composition, and even its fate. Every pixel of that ancient light holds a clue about how the cosmos evolved from simple plasma to complex galaxies. It is a message from the beginning, still traveling through space, still whispering the story of creation to anyone who listens. From chaos came simplicity. From simplicity came order. And from order, one day, would come light once again, brighter and stronger than before. The first atoms had formed, The first light had been released, and the stage was set for the birth of stars. In the next part, we will enter that age, the cosmic dawn, when gravity ignited the first suns, ending the dark ages and bringing light back to the universe for the second time. For hundreds of millions of years after the Big Bang, the universe existed in silence. The fog had cleared, the light of the cosmic background had faded to a cold whisper, and darkness filled the vast, expanding space. There were no stars, no galaxies, only immense clouds of hydrogen and helium drifting through the void. It was a calm universe, but it was not yet alive. Gravity, however, was patient. Wherever the early universe contained slightly more matter, even a tiny fraction denser than its surroundings, those regions began to pull in more gas. The process was slow, but inevitable. Over millions of years, the invisible web of gravity gathered matter into filaments and nodes. These regions grew denser and hotter as hydrogen atoms collided under immense pressure. Eventually, in those dense pockets, the temperature rose to about 10 million degrees Kelvin. At that point, the simplest element in the universe, hydrogen, began to fuse into helium. The energy released by that fusion lit up the darkness. The first stars had been born. These early stars, known as population 3 stars, were unlike the ones we see today. They contained almost no heavy elements, only hydrogen and helium. And as a result, they were enormous. Many were hundreds of times the mass of our sun. Because of their size, they burned their fuel quickly, living short but brilliant lives. They shone with an intense blue-white light, flooding the universe with radiation that began to reionize the surrounding gas. This era, known as the cosmic dawn, ended the universe's long dark ages. For the first time since the Big Bang, light returned, not from a uniform background, but from countless individual points scattered across space. The universe had become illuminated once again, and structure began to grow. The light from these first stars did more than brighten the cosmos. It changed it. Their radiation stripped electrons from nearby atoms, reionizing the gas that filled space. This process made the universe transparent once more, allowing light to travel freely and laying the groundwork for the formation of galaxies. But the first stars were not eternal. Massive and unstable, they quickly exhausted their fuel. Within only a few million years, they exploded as supernovae, releasing enormous amounts of energy and scattering newly forged elements into the surrounding space: carbon, oxygen, nitrogen, and iron. These were the first heavy elements in the universe, the essential ingredients for planets and life. In their deaths, the first stars seeded the cosmos with possibility. Their remnants, black holes and neutron stars, became anchors for new clouds of gas to gather around. Gravity pulled those enriched materials together again, and over time, new generations of stars formed. Smaller, longer-lived, and more complex. Clusters of these stars began to gather into vast rotating structures, the first galaxies. What had once been a universe of darkness and simplicity had transformed into one filled with light and variety. The process of star birth and death became the cosmic heartbeat that continues today. Astronomers studying this period look back across billions of years using powerful telescopes like the James Webb Space Telescope, capable of detecting the faint infrared glow from those ancient suns. Each observation reveals more about how the universe transitioned from darkness to light. Some of the galaxies we can see today began forming less than 400 million years after the Big Bang, a blink in cosmic time. The first stars also played another important role. Their radiation helped heat the surrounding gas, influencing how later galaxies and clusters would form. Without them, the universe might have remained dark and uniform. With them, it became structured, filled with the beginnings of the cosmic web that still defines its shape. From that point forward, the universe entered an era of creativity. Stars formed in groups, galaxies collided and merged, and the first black holes began to grow in their centers. Space had gone from stillness to motion, from silence to symphony. The age of darkness had ended. The stars had returned, not just as lights in the sky, but as the forges of all elements, the engines of complexity, and the storytellers of time. In the next part, we'll follow their legacy, how the first galaxies assembled, how the structure spread across the universe, and how gravity continued to sculpt the grand design of the cosmos. The light from the first stars spread through space, illuminating clouds of hydrogen and helium that had been drifting since the earliest times. But those stars were only the beginning. Gravity continued to pull matter together, linking small clusters into larger structures. From these growing networks, the first galaxies were born. The early universe was not uniform. The tiny fluctuations left behind in the cosmic microwave background, those slight variations in temperature and density, acted as the seeds of cosmic architecture. Wherever the universe was just a little denser, gravity gained an advantage. Those areas attracted more gas, while slightly thinner regions became emptier. Over millions of years, these differences amplified. Simulations and observations show that matter began to arrange itself into a cosmic web, a vast three-dimensional network of filaments and nodes stretching across space. The filaments were made mostly of dark matter, an invisible substance that interacts through gravity but not with light. Ordinary matter, the kind that forms stars and planets, followed this hidden scaffolding, gathering along the same lines. At the intersections of these filaments, gas condensed into the first proto-galaxies. Small, irregular collections of stars and gas clouds. Many were chaotic and turbulent, colliding often as gravity pulled them together. Over time, these mergers created larger, more stable galaxies, including the ancestors of the spiral and elliptical galaxies we see today. The process was gradual but relentless. When two small galaxies collided, their stars passed through each other mostly unharmed, but their gas clouds crashed and compressed, triggering bursts of star formation. These starburst galaxies shone brightly, sometimes producing thousands of new stars in just a few million years. The universe was busy building itself. Within 1 billion years after the Big Bang, the first fully formed galaxies had appeared. They varied in shape and size. Some were compact spheres, others thin rotating disks. The spiral pattern familiar to us today began as a natural result of angular momentum, as gas cooled and flattened under its own rotation. Gravity shaped them, but time refined them. Dark matter remained the quiet architect behind this growth. Without it, galaxies would not have formed so quickly. It made up about 85% of all matter in the universe, its invisible gravity, drawing ordinary matter into clusters. Even now, each galaxy, including our own Milky Way, sits within a massive halo of dark matter that extends far beyond its visible stars. The universe's large-scale structure, billions of galaxies, forming filaments hundreds of millions of light-years long, still follows that same pattern today. Between the filaments lie vast empty regions called voids, cosmic deserts nearly devoid of galaxies. Together, this web of filaments and voids gives the universe its grand texture, a design both intricate and balanced. The galaxies themselves were the engines of transformation. Inside them, the first generations of stars lived and died, producing heavy elements that enriched the gas around them. Each new cycle of star birth added complexity, forming planets, moons, and the chemistry needed for life. By about 1 billion years after the Big Bang, the universe had entered what astronomers call the epoch of reionization. The light from countless new stars and galaxies ionized the remaining hydrogen in space, turning the universe fully transparent. The fog of its youth had finally lifted. From that point onward, the cosmic web grew ever larger. Galaxies formed groups and clusters, bound by gravity into immense structures stretching across millions of light years. Some merged into superclusters, colossal chains of galaxies connected like glowing pearls across the dark. Even now, 13.8 billion years later, the same processes continue. Galaxies collide and merge. Stars are born and die, and the universe expands around them all. The Milky Way itself is part of a vast system known as the Laniakea supercluster, which contains over 100,000 galaxies, one small thread in the endless fabric of the cosmos. The formation of the cosmic web marked a new chapter. The universe had structure, movement, and complexity. It was no longer a quiet cloud of gas, but a living system, dynamic, evolving, and filled with light. In the next part, we'll focus on one of the most extraordinary consequences of that evolution: the birth of supermassive black holes at the centers of galaxies, and how they helped shape the universe we see today. As the first galaxies took shape, another kind of structure began to form deep within their hearts, invisible, powerful, and profoundly influential. These were the first black holes, objects so dense that nothing, not even light, could escape their gravity. Astronomers believe that black holes appeared very early in cosmic history, perhaps only a few 100 million years after the Big Bang. Some were born from the collapse of the universe's first massive stars, those enormous, short-lived population 3 stars that ended their lives in spectacular explosions. When their nuclear fuel ran out, gravity won the battle against pressure. The star's core collapsed inward, forming a singularity, a region where density and gravity became infinite. But some black holes formed on a much larger scale and much faster than expected. Observations show that by the time the universe was less than 1 billion years old, there already existed supermassive black holes, millions or even billions of times the mass of our sun. How they grew so quickly remains one of cosmology's great mysteries. One idea suggests that these giants were born from direct collapse, huge clouds of primordial gas falling inward under gravity without forming stars first. Another possibility is that smaller black holes merged repeatedly, growing rapidly in dense early galaxies. However they formed, their presence began to shape the universe in profound ways. At first glance, black holes seem like destroyers, swallowing light, matter, and time itself. And time itself. Yet in cosmic evolution, they are also creators. When matter falls toward a black hole, it doesn't simply disappear. Before crossing the event horizon, the boundary beyond which nothing returns, the infalling gas forms a spinning accretion disk, heating up to millions of degrees. This process releases enormous amounts of energy, outshining entire galaxies. These brilliant regions are known as quasars, the most luminous objects in the universe. For a time, many young galaxies hosted quasars at their centers, each powered by a growing supermassive black hole. Their intense radiation illuminated the universe's early ages, and their jets of energy helped shape the gas and stars around them. The activity of these early black holes influenced how galaxies evolved. When a quasar blazed, it could push gas out of its host galaxy, slowing star formation. When it dimmed, gas could fall back in, forming new generations of stars. This balance, between gravity pulling in and radiation pushing out, created a kind of feedback loop that regulated galactic growth. Today, astronomers know that nearly every large galaxy including our Milky Way, contains a supermassive black hole at its center. The one in our galaxy, called Sagittarius A, is about 4 million times the mass of the Sun. It lies quietly at the core, influencing the orbits of nearby stars, but currently consuming very little material. In other galaxies, black holes remain far more active, still shaping their environments billions of years after their birth. The connection between black holes and galaxies is deep. Observations show that the mass of a galaxy's central black hole is closely related to the total mass of its stars. This relationship suggests that galaxies and their black holes grew together, each affecting the other's fate over billions of years. These invisible giants also leave their mark in more subtle ways. When two galaxies merge, their central black holes spiral toward each other, eventually combining in a burst of gravitational waves, ripples in space-time first predicted by Einstein and observed directly in 2015. Every such merger sends a faint vibration through the universe, a signal of creation through destruction. In this way, black holes, once thought to be the universe's dead ends, are now seen as vital parts of its ongoing evolution. They help sculpt the galaxies, regulate star formation, and distribute energy across space. Without them, the universe would be far quieter, dimmer, and less structured than it is today. As time passed, galaxies settled into familiar shapes, spirals, ellipticals, and irregular forms. The largest grew by merging with smaller neighbors, while stars continued to live, shine, and die within them. The early chaos had transformed into the grand, ordered universe we now observe. In the next part, we'll leave the centers of galaxies and look outward, exploring how stars like our Sun formed, how planetary systems emerged from clouds of dust, and how the same processes that began after the Big Bang eventually led to worlds capable of life. By the time the universe was a few billion years old, it had transformed from a smooth sea of gas into a vast collection of galaxies, each containing billions of stars. But not all stars were the same. The earliest ones, those huge, short-lived population-3 giants, had already lived, burned, and died, enriching the surrounding space with heavier elements. Their explosions spread carbon, oxygen, iron, silicon, and other building blocks of life across the interstellar medium. These elements changed everything. The next generation of stars, known as Population 2 and later Population Y, formed from this enriched gas. Unlike the first stars, they contained traces of heavier atoms that made their formation more efficient and their lives more stable. Many of these stars were smaller and longer lived, capable of burning steadily for billions of years. Our own Sun belongs to this later generation. Stars are born inside molecular clouds, enormous regions of cold, dense gas and dust. Drifting through galaxies, gravity slowly pulls parts of these clouds inward, compressing them until their centers heat up. When temperatures reach about 10 million degrees Kelvin, nuclear fusion begins and a star ignites. The surrounding material forms a protoplanetary disk, a flat ring of gas and dust orbiting the newborn star. Within those disks, tiny particles collide, stick together, and gradually grow into planets. In the early universe, these processes repeated everywhere. New stars lit up along the spiral arms of galaxies, creating waves of light and heat. Around many of them, planetary systems began to form. Each system was unique, shaped by the amount of material available, the chemistry of its elements, and the gravitational balance of its star. Our solar system began about 4.6 billion years ago, roughly 9 billion years after the Big Bang. A giant cloud of gas and dust, likely enriched by a nearby supernova, collapsed under its own gravity. At its center, the Sun was born. Around it, leftover material flattened into a disk, And over tens of millions of years, the planets emerged. The inner ones, Mercury, Venus, Earth, and Mars, formed from rocky material that could withstand the heat near the young sun. Farther out, gases condensed to form Jupiter, Saturn, Uranus, and Neptune. This sequence, star birth, element creation, planet formation, is one of the universe's most elegant cycles. Stars create elements. Those elements form planets. Planets, in turn, can host life, which one day looks back and studies the stars that made it possible. The chemistry of space tells this story clearly. Spectra from distant galaxies show the same elements found in our world: hydrogen, helium, carbon, oxygen, nitrogen, and iron. Every atom in your body once passed through the heart of a star. In a literal sense, we are made of stardust, fragments of ancient suns reborn in new forms. As galaxies evolved, star formation continued at different rates. About 10 billion years ago, the universe reached its peak of star formation, a time sometimes called the cosmic noon. Galaxies were rich with gas, glowing with the light of countless young stars. After that period, the available gas began to thin out as stars converted more and more of it into heavier elements. The rate of new star formation slowed, and galaxies aged gracefully, their colors shifting from blue to golden red. In the Milky Way, this process still continues. New stars form in regions like the Orion Nebula, where gravity and radiation balance in delicate harmony. Yet most of the stars we see tonight are already billions of years old, their light traveling through time to reach us. The birth of stars like the sun marked a turning point in cosmic history. For the first time, the universe produced long-lived, stable environments where complex chemistry could flourish. Around some of these stars, planets cooled enough for liquid water to exist, and with it, the potential for life. Every galaxy, every cluster, every region of space now contains countless suns, each with its own story. Some host gas giants, others rocky worlds, some perhaps barren, and others may be alive. The same physical laws that govern the first atoms after the Big Bang still guide these processes today. From this point onward, the universe became not only a place of light, but also a place of possibility. The same gravity that once drew hydrogen into stars now shapes worlds, moons, and atmospheres. In its quiet persistence, the universe built the framework for existence itself, from simple particles to the complex web of life that would one day try to understand how to understand. It all began. In the next part, we'll move closer to home, to the formation of our own galaxy, the Milky Way, and how it became the island of stars we inhabit today within the ever-expanding universe. Our home galaxy, the Milky Way, is one of the most remarkable results of the universe's long process of organization. Its story began more than 13 billion years ago, when the cosmos was still young, and galaxies were small, irregular, and often chaotic. The Milky Way did not appear all at once. It grew slowly, through countless mergers, collisions, and the steady pull of gravity that gathered stars, gas, and dark matter into a single spiral system. In the early universe, small clumps of dark matter acted as the foundation for galaxy formation. These invisible structures drew in gas from the surrounding space. Within those halos, the first stars ignited, forming tiny proto-galaxies. Over hundreds of millions of years, gravity pulled these small galaxies together. They collided, merged, and reshaped one another, eventually forming larger, more stable systems. The Milky Way likely began as one of these early proto-galaxies. Through a long sequence of mergers, perhaps dozens or even hundreds, gradually grew to the massive spiral we see today. Spanning about 100,000 light-years across, and containing more than 200 billion stars. At its heart lies a dense bulge of older stars and a supermassive black hole known as Sagittarius IK. Around it, the galaxy's thin, rotating disk stretches outward, filled with younger stars, clusters, and swirling nebulae where new suns are still being born. Surrounding it all is a vast, nearly spherical halo of dark matter that provides the gravitational framework keeping everything bound together. Astronomers have pieced together this history by studying the motion and composition of stars. Older stars, rich in hydrogen and helium, but poor in heavier elements, reveal the galaxy's ancient beginnings. Younger stars, with higher metallicity, show how generations of stellar birth and death enriched the Milky Way over time. The Milky Way is not isolated. It belongs to a small collection of galaxies called the Local Group, which includes about 50 members. The largest are our own galaxy and the Andromeda Galaxy, followed by the Triangulum Galaxy and dozens of smaller dwarf galaxies. These systems are connected by gravity, slowly moving toward one another as they orbit a common center. In about 4 billion years, the Milky Way and Andromeda will collide. This future event, already predicted by observations, will not be a violent explosion but a slow, graceful merging. The stars in each galaxy are so far apart that they will rarely collide directly. Instead, the galaxies will pass through each other, their shapes warping and stretching under mutual gravity. Over time, they will settle into a new, larger elliptical galaxy, sometimes called Milkomeda, with a combined black hole at its center. Within our galaxy, the cycles of creation and destruction continue. Giant molecular clouds give birth to new stars, while supernovae enrich the surrounding gas with heavier elements. The Milky Way's spiral arms, bright with young blue stars, rotate around the galactic center every 230 million years. Our sun, orbiting along one of these arms, has completed about 20 such journeys since it formed. The scale of our home is difficult to grasp. Light takes 8 minutes to travel from the sun to Earth, but more than 26,000 years to reach us from the galactic center. The faint band we call the Milky Way in the night sky is just a small part of the disk, a sideways view of billions of distant suns blending into a soft, silvery glow. Beyond the Local Group lies an even greater structure, the Virgo supercluster, a vast region containing thousands of galaxies, all moving together through space. The Milky Way is just one spiral among them, a quiet member of an enormous cosmic family. Our galaxy's formation mirrors the universe's broader story, from simplicity to complexity, from scattered matter to organized beauty. Every star, planet, and molecule here exists because of billions of years of gradual change guided by the laws of physics and the pull of gravity. When we look up at the stars, we are seeing not only light from other worlds, but also evidence of our own origin, fragments of a process that began long before Earth existed. The Milky Way is both our home and our history, a living record of cosmic evolution written in starlight. In the next part, we'll explore how the universe continued to evolve after galaxies like ours settled into form, how expansion shaped the cosmos on the largest scales, and how dark matter and dark energy began to determine its ultimate fate. As galaxies like the Milky Way formed and matured, the universe itself continued to stretch. What began as expansion during the Big Bang did not stop when galaxies took shape. It kept going, slowly but steadily, carrying clusters of galaxies farther apart with time. This expansion is not movement through space. It is the stretching of space itself, the quiet rhythm of the cosmos growing older. Astronomers first discovered this motion in the early 20th century. When Edwin Hubble observed distant galaxies, he noticed something remarkable. Their light was shifted toward the red end of the spectrum, a phenomenon known as redshift. The farther away a galaxy was, the more its light was stretched, clear evidence that space between galaxies was expanding. This relationship, now called Hubble's law, revealed that the universe was not static, but dynamic, still unfolding from its beginning. At first, scientists assumed that the expansion would gradually slow down. Gravity, pulling all matter inward, should have been enough to resist it over time. Yet in the late 1990s, observations of distant type Ia supernovae, exploding stars used as standard candles, revealed something astonishing. The universe's expansion wasn't slowing, it was accelerating. To explain this, cosmologists propose the existence of a mysterious force called dark energy. It acts like a repulsive pressure built into space itself, driving galaxies apart, faster and faster. Today, dark energy is thought to make up about 68% of the total energy content of the universe. Dark energy is not the only hidden component of the cosmos. Roughly 27% of it consists of dark matter, an invisible form of matter that doesn't emit, absorb, or reflect light, but exerts gravity. Only about 5% of the universe is made of ordinary matter, the atoms that form stars, planets, and life. In other words, everything we can see is only a tiny fraction of what truly exists. The evidence for dark matter is overwhelming. Galaxies rotate faster than visible mass alone can account for. Clusters of galaxies bend light through gravitational lensing more strongly than expected. The cosmic web itself could not have formed as quickly as it did without the additional gravitational pull of dark matter. It acts as the invisible framework upon which all cosmic structure is built. Yet no one knows exactly what dark matter is. It might consist of unknown particles, perhaps WIMPs, weakly interacting massive particles, or it might be something entirely different, a property of gravity we have not yet understood. Despite decades of searching, dark matter has not been detected directly. Its presence is known only through its gravitational effects. Dark energy is even more mysterious. Some theories describe it as a constant energy density filling space, known as the cosmological constant, first introduced by Einstein. Others suggest it could be a dynamic field that changes over time. Whatever its nature, dark energy determines the universe's long-term fate. If dark energy remains constant, the expansion will continue to accelerate indefinitely. Galaxies will drift farther apart until, in the distant future, most will vanish beyond our cosmic horizon. Their light stretch to invisibility. The night sky will grow emptier, with only the stars of our local group remaining. These discoveries have changed how humanity understands its place in the cosmos. For centuries, we imagined the universe as a fixed stage where celestial bodies moved predictably. Now we know it is alive in motion, expanding, evolving, and driven by forces we barely comprehend. The accelerating expansion is gentle on human timescales. It will take billions of years for distant galaxies to fade completely from view. But the fact that space itself is stretching faster each moment reminds us that the universe is not static, but dynamic, and that the story of creation is still unfolding. The cosmic expansion tells a subtle truth. Even as everything moves apart, the laws of physics remain constant everywhere. The same gravity that binds galaxies, the same light that travels across billions of years, the same elements that form life, all follow the same principles. In this vast growing universe, order persists amid change. In the next part, we'll explore how scientists measure this expansion, the tools, telescopes, and methods that allow us to read the universe's history, and what those measurements reveal about its ultimate beginning. To understand how the universe began, scientists first needed to learn how fast it is expanding today. That measurement, the rate at which galaxies move apart, acts like a cosmic clock, allowing astronomers to trace the history of the universe backward through time. Every observation, every calculation, brings us one step closer to the very first moment. The expansion rate is described by the Hubble constant, a number that tells how many kilometers per second galaxies move away for each megaparsec of distance. Edwin Hubble first estimated it in 1929 using visible light from nearby galaxies, though his tools were crude by modern standards. Over the decades, better instruments refined that value again and again. Today, scientists use several independent methods to measure it. One of the most direct is observing Cepheid variable stars, pulsating stars whose brightness changes at regular intervals. Because the period of their pulsation is related to their true luminosity, astronomers can determine their distance precisely. Comparing that distance to how much their light is redshifted reveals the expansion rate. Another powerful tool is Type Ia supernovae, exploding stars that always reach nearly the same peak brightness. They act as cosmic lighthouses, visible across billions of light years. By comparing their apparent brightness with their known luminosity, scientists can map how expansion has changed over time. A completely different approach comes from the cosmic microwave background, CMB, the afterglow of the Big Bang. Satellites such as COBE, DOMAP, and Planck have measured tiny fluctuations in that ancient light. By analyzing those patterns, cosmologists can infer how fast the universe was expanding when it was only 380,000 years old and project that right forward to the present day. Curiously, these two methods, one based on the nearby universe and one based on the early universe, do not give exactly the same result. The difference, known as the Hubble tension, remains one of the greatest mysteries in modern cosmology. It may point to unknown physics beyond our current models, perhaps new particles, new interactions, or subtle variations in dark energy over time. Despite this uncertainty, all measurements tell the same broad story. The universe has been expanding for 13.8 billion years, and that expansion is accelerating. The data allow cosmologists to reconstruct a detailed timeline. From the Big Bang through the formation of atoms, galaxies, and planets, to the cosmic web we observe today. Measuring the expansion is like reading the universe's memory. Every galaxy's redshift is a timestamp, every photon a record of the past. The farther away we look, the younger the universe appears. When we observe a galaxy 10 billion light-years distant, we see it as it was 10 billion years ago. Our telescopes are not just instruments of sight, they are instruments of time. Modern technology has refined this cosmic archaeology to an astonishing degree. Telescopes like Hubble, James Webb, and the Vera Rubin Observatory capture light that has traveled almost the entire age of the universe. Each image they take is a snapshot of an earlier chapter in cosmic history. By assembling those snapshots, scientists can piece together the full story of creation. Even the tiniest fluctuations in temperature or density within the CMB provide precise information about the universe's age, composition, and geometry. They confirm that space is nearly flat, that dark matter and dark energy dominate its contents, and that the Big Bang model accurately describes its evolution from a hot, dense beginning. Through these measurements, the early universe becomes more than theory. It becomes a map, a sequence of events defined by light, distance, and time. From this map, scientists can run the cosmic clock backward, all the way to that first fraction of a second when energy became matter and the laws of physics took form. Every number, every constant, every faint signal from the edge of space helps us refine our understanding of the beginning. The more precisely we measure the present, the more clearly we can see the past. The universe, in its vastness, offers no written record, only light, and we have learned to read it. In the next part, we will turn that cosmic clock all the way back to the earliest Measurable moment. When the laws of physics first emerged and time itself began to flow. To reach the beginning of time, we must enter a realm where ordinary physics begins to dissolve, a fraction of a second so short that our most advanced equations strain to describe it. This is the earliest measurable era of the universe, the instant when the laws of nature themselves were born. In the very first 10 seconds, known as the Planck time, all the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified. Temperatures reached 1032 Kelvin, and space was smaller than a subatomic particle. At that scale, quantum effects of gravity dominated, meaning that space and time themselves fluctuated wildly, blending into something that cannot be described by classical geometry. Physicists have long sought a theory of quantum gravity to describe this era, a framework that merges general relativity, which explains gravity on cosmic scales, with quantum mechanics, which governs the subatomic world. Candidates such as string theory and loop quantum gravity propose that the fabric of space is not continuous but made of tiny, vibrating entities or loops. Yet direct evidence remains elusive. What we do know is what came next. At around 10 nanoseconds, the universe underwent a sudden burst of expansion called cosmic inflation. Space itself stretched exponentially, growing by a factor of at least 1026 in less than the blink of an eye. This expansion smoothed out irregularities, flattened space, and set the initial conditions for everything that followed. Inflation also magnified quantum fluctuations, tiny variations in energy that existed at microscopic scales, into the seeds of galaxies and clusters. These minuscule differences in density eventually grew, under the influence of gravity, into the vast cosmic web we observe today. The uniformity of the cosmic microwave background, with its delicate patterns, is the fingerprint of those amplified fluctuations. When inflation ended, its driving energy transformed into an enormous bath of particles and radiation in a process called reheating. The universe was unimaginably hot and dense, filled with a plasma of quarks, gluons, electrons, positrons, and neutrinos. It was expanding rapidly, but beginning to cool. The first split between forces had already begun. Gravity separated from the others, followed by the division of the strong nuclear force from the electroweak force. By 10 seconds, the universe entered the electroweak epoch. At this point, the electromagnetic and weak nuclear forces split, leaving the 4 fundamental interactions as we know them today. This symmetry breaking was one of the universe's first transformations, a moment when energy differences in the vacuum gave rise to distinct physical behaviors, a subtle shift that would define how matter and light interact forever. During this time, the universe was still far too energetic for stable particles. Matter and antimatter existed in almost equal quantities, annihilating each other as fast as they formed. Yet somehow, for reasons not yet fully understood, there was a slight imbalance, roughly 1 extra particle of matter for every billion pairs of matter and antimatter. When the annihilation ended, those few survivors became the matter that makes up everything in the cosmos today. As expansion continued, the universe cooled below 1 trillion degrees Kelvin. Quarks began to combine into protons and neutrons, the building blocks of atomic nuclei. The balance between light and matter was still dominated by photons. For every proton, there were 1 billion photons racing through space. But matter, small in quantity though it was, had taken hold. This first second of existence defined the rules of everything that would come afterward. Space expanded, time moved forward, forces took shape, and matter gained its fragile foothold. The universe had gone from something unknowable to something measurable, from quantum chaos to physical order. What happened before the Planck time remains beyond our reach. Perhaps the universe emerged from a quantum fluctuation in an earlier cosmos, or perhaps time itself began with that first instant. Whatever the answer, the laws that arose in those first moments have never changed. The same constants that define the newborn universe still guide galaxies, stars, and life. In the next part, we'll continue along that early timeline, exploring how those first particles fused into the lightest elements, how the cosmic chemistry began, and how the ingredients of everything that exists today were forged in the universe's first minutes. About 1 second after the Big Bang, the universe was a dense glowing ocean of particles and radiation. Temperatures were still near 10 billion degrees, but as space expanded, that heat began to fade. In this brief window of cooling, something profound occurred. The first chemical reactions in history, the forging of the universe's earliest elements. This process, known as Big Bang nucleosynthesis, took place between roughly 1 second and 20 minutes after the beginning. During this time, the newborn universe acted as a giant nuclear reactor. Protons and neutrons collided and fused, forming the first stable atomic nuclei. At first, nearly all matter existed as hydrogen. Single protons, but collisions between those protons and neutrons created heavier isotopes. The earliest product was deuterium, a hydrogen nucleus with 1 proton and 1 neutron. As more particles joined, deuterium fused into helium-3 and helium-4 A small fraction went on to form lithium and beryllium, though most of those heavier nuclei were unstable and decayed. The result of this process defined the basic chemical makeup of the universe, about 75% hydrogen and 25% helium by mass, with traces of lithium. These proportions match what astronomers still observe today in the oldest stars and galaxies, providing strong evidence for the Big Bang model. But this cosmic chemistry ended quickly. As the universe continued to expand, temperatures dropped below the threshold needed for fusion. Within 20 minutes, nuclear reactions ceased. The light elements that formed in that brief period would remain unchanged for hundreds of millions of years, until the first stars lit up and created heavier elements through stellar fusion. Those first elements were more than just numbers in a cosmic formula. They were the foundation of everything that would follow. Hydrogen would fuel the stars. Helium would fill the hearts of galaxies. Lithium would seed early chemistry. The entire structure of the universe, from the stars in the night sky to the water in our cells, began with those few simple nuclei forged in the Big Bang's afterglow. The universe at this stage was still opaque, filled with radiation that scattered off free electrons. Light could not yet move freely, but the matter within it had begun to organize. Tiny fluctuations in density, the faint differences left over from inflation, determined where gas would later condense, forming stars and galaxies. The process of nucleosynthesis also revealed the remarkable precision of the universe's physical laws. If the ratio of protons to neutrons had been slightly different, the amounts of hydrogen and helium would have changed dramatically. If the universe had expanded faster, there would have been no time for fusion. Slower, and everything might have collapsed back on itself. Somehow, the constants of nature balanced perfectly to allow complexity to emerge. By the end of nucleosynthesis, the universe was only a few minutes old. It had cooled enough that nuclear reactions had stopped, but it was still far too hot for atoms to exist. For the next several 100,000 years, protons and electrons remained free, colliding constantly in a bright, dense plasma dipole. The light from that period still echoes across space as the cosmic microwave background, the silent memory of the first elements being born. From that moment onward, the universe's story would shift from creation to transformation. The next great chapter would belong to gravity, the slow, patient force that would gather these simple ingredients into stars, ignite new kinds of fusion, and begin the long process of turning hydrogen into everything else. In the next part, we will follow that transformation, how the first stars became the universe's second forge, creating carbon, oxygen, and the elements that would one day make planets, oceans, and life itself. When the universe was still young, its chemistry was simple. It contained hydrogen, helium, and a faint trace of lithium. Nothing more. These light elements filled the darkness like an unfinished song waiting for its next verse. For anything more complex to exist, carbon, oxygen, nitrogen, iron, the universe needed a new kind of furnace. That furnace would be the stars. Hundreds of millions of years after the Big Bang, gravity began gathering hydrogen and helium into great clouds. In their centers, pressure and temperature rose until hydrogen nuclei fused into helium, releasing light and heat. Thus, the first generation of stars was born. These early stars were immense, some hundreds of times the mass of our sun, and they burned fiercely. Inside their cores, nuclear fusion continued beyond hydrogen. When the supply of hydrogen ran out, the core collapsed and heated further, allowing helium to fuse into heavier elements, carbon and oxygen. In even more massive stars, the fusion process continued, layer by layer, creating neon, magnesium, silicon, and finally iron. But fusion could not go beyond iron. Creating heavier elements required more energy than it produced. When a massive star reached that limit, its balance between pressure and gravity broke. In an instant, the star's core collapsed, and the outer layers exploded outward in a supernova, one of the most powerful events in the universe. In that brief explosion, temperatures soared high enough to forge elements heavier than iron. Gold, silver, uranium, platinum, and others. The supernova scattered these new elements into space, enriching the surrounding gas clouds. Each explosion seeded the cosmos with the ingredients of planets, oceans, and life. These materials did not vanish. Gravity eventually gathered them again into new clouds, which collapsed into new generations of stars. Around those stars, dust and gas formed disks, and within those disks, new planets emerged. Every rock, every grain of sand, every molecule of water, all of it once belonged to the heart of a star that lived and died billions of years ago. This cycle of thought, creation and destruction, stellar birth, fusion, explosion, and rebirth, built the chemical diversity we see today. Astronomers call it stellar nucleosynthesis, the process by which stars act as cosmic alchemists, turning simple hydrogen into the full periodic table of elements. Our own sun is a later generation star, born from the remnants of many supernovae. The carbon in our cells, the calcium in our bones, the oxygen we breathe, all forged long before the Earth existed. When we look at the night sky, we are seeing not only distant suns, but also the past lives of the stars that the stars made us possible. The rhythm of stellar evolution continues even now. Massive stars live short, brilliant lives and end as supernovae or black holes. Smaller stars, like our sun, burn for billions of years, eventually shedding their outer layers to form glowing shells called planetary nebulae. Their cores shrink into white dwarfs, cooling slowly over trillions of years. In time, even though heavy elements created by these processes drift through space, joining new generations of gas and dust. The universe is a vast recycling system, endlessly transforming itself. What dies in one era becomes the seed of creation in the next. The stars did more than fill the universe with light. They gave it complexity, structure, and the raw materials for life. Through their long lives and violent deaths, they bridged the gap between simplicity and meaning, between a cosmos of pure energy and one capable of thought. In the next part, we'll move from the chemistry of stars to the architecture of the galaxies, how these enormous systems grew together, how they interact, and how they continue to shape the universe's evolution even now. As the first generations of stars lived and died, their light and energy began to shape the structure of the universe. Gravity was the quiet sculptor behind it all, pulling together clouds of gas, clusters of stars, and dark matter into vast rotating systems. The galaxies. Over billions of years, these galaxies became the building blocks of the universe, each one a small island of order floating in the expanding sea of space. The earliest galaxies were small, irregular clumps of stars and gas. They formed where the density of matter was slightly higher than average, along the invisible filaments of dark matter that stretched through space. As time passed, these galaxies collided and merged, combining their stars and gas into larger systems. Some grew into majestic spiral galaxies, others became rounded ellipticals, and some remained chaotic and irregular. The Milky Way, our home galaxy, is the result of such a process, a long history of mergers, collapses, and slow evolution guided by gravity. Every galaxy tells a similar story. When two galaxies collide, their stars rarely crash into one another directly. The distances between them are far too great. Instead, their mutual gravity warps and stretches them, flinging out long tails of stars and gas. Over time, the systems settle into new shapes, often triggering waves of star formation in the process. This cosmic dance of collisions is not rare, but constant. Galaxies grow by merging with smaller neighbors, an endless process that continues even today. In the observable universe, there are estimated to be more than 2 trillion galaxies, each containing anywhere from a few million to several trillion stars. Together, they form an immense pattern known as the cosmic web, a network of filaments and clusters connected by gravity and separated by enormous voids. Within this web, galaxies gather in clusters, groups containing hundreds or thousands of members, which in turn form even larger superclusters. These colossal structures span hundreds of millions of light years, their shapes revealing how the universe has evolved since the Big Bang. When astronomers map these structures, they find something remarkable. The large-scale pattern of galaxies matches almost perfectly the tiny fluctuations seen in the cosmic microwave background. The seeds of the cosmic web were present from the beginning, written into the fabric of space itself. Each galaxy is a world unto itself. Some, like the Milky Way and Andromeda, are rich with spiral arms filled with young blue stars. Others, like giant ellipticals, are ancient and red, their star formation long finished. Some galaxies host quasars, active supermassive black holes at their centers that outshine all their surrounding stars combined. Others are quiet, glowing softly with the combined light of billions of suns. Galaxies are not static objects. They spin, evolve, and change over billions of years. Spiral arms wind and unwind. Central black holes grow, and stars drift slowly through orbits. That can take hundreds of millions of years to complete. From a cosmic perspective, each galaxy is alive, forming, aging, and transforming in rhythm with the universe itself. Our own Milky Way is part of the local group, a small neighborhood of about 50 galaxies bound by gravity. The nearest, large one, Andromeda, is about 2.5 million light-years away, and it's moving toward us. In roughly 4 billion years, the two will merge, forming a single, massive, elliptical galaxy. The night sky of that distant future will be filled with countless new stars as the galaxies intertwine. Beyond the local group lies the Virgo supercluster, home to thousands of galaxies, and beyond that, the Laniakea supercluster, a vast region containing hundreds of thousands more. These immense formations are connected through filaments of gas and dark matter, stretching across the cosmos like threads in an infinite tapestry. Despite the immensity of the structure, the universe remains governed by the same simple laws. Gravity draws matter together, while dark energy drives expansion apart. Between these two forces, a delicate balance exists, a cosmic dance that has lasted for nearly 14 billion years. Each galaxy, each cluster, each strand of the cosmic web is a note in the universe's grand composition. From a distance, the pattern appears serene, but up close, it is full of motion and change. The light from distant galaxies tells us that this dance has been ongoing since the first stars formed, a rhythm that continues, guiding the universe toward its unknowable future. In the next part, we'll look deeper into that balance. How gravity, expansion, and dark energy together shape the ultimate fate of the universe, and what may happen to galaxies, stars, and space itself as time stretches endlessly forward. Every story that begins must one day move toward an end, and the universe, vast and ancient as it is no exception. From the moment of the Big Bang, expansion has carried galaxies apart, and that motion has continued for nearly 14 billion years. But what happens next? Will the universe expand forever, slow down and collapse, or fade into darkness? The answer depends on the delicate balance between gravity, dark energy, and time itself. For most of human history, scientists assumed the universe would eventually stop expanding. Gravity, they thought, would pull all matter back together, leading to a final collapse, a big crunch. In that scenario, the galaxies would slow, reverse direction, and fall inward, their stars colliding as space itself shrank. Temperatures would rise again, until everything returned to the same dense, hot state that began it all. Some even imagined that this might repeat forever, an eternal cycle of birth and rebirth. But in the late 20th century, a different picture emerged. Observations of distant supernovae revealed that the universe's expansion isn't slowing down, it's speeding up. Some mysterious force, which we now call dark energy, is pushing galaxies apart faster than gravity can pull them together. It acts like a quiet, invisible pressure built into space itself, and it grows stronger as the universe expands. If dark energy remains constant, the universe will continue to expand forever. Galaxies not gravitationally bound to each other will drift apart until their light can no longer reach us. Over tens of billions of years, only the galaxies of our local group, the Milky Way, Andromeda, and a few smaller companions will remain visible. Everything else will vanish beyond the cosmic horizon, their light stretched into invisibility by the accelerating expansion of space. Inside those remaining galaxies, stars will keep shining for trillions of years. But even stars have limits. The largest will burn out first, collapsing into black holes or scattering their elements into space. Smaller, longer-lived stars like red dwarfs will glow faintly for far longer, some for 1,000 times the current age of the universe, before they too fade. As the ages pass, new star formation will slow and eventually stop. Gas clouds will be exhausted, and the last bright stars will cool into dim embers. The universe will enter the degenerate era, when the only remaining objects are white dwarfs, neutron stars, and black holes, silent remnants of what once was. Over unimaginable timescales, even those remnants will change. White dwarfs will cool into black dwarfs, completely dark and cold. Galaxies will drift apart into isolated islands surrounded by emptiness. Occasionally, two dead stars may collide, or a black hole may consume a passing object, briefly releasing light. Flickers of activity in an otherwise silent cosmos. Far beyond that, perhaps after 10 years or more, even black holes will begin to evaporate through a process called Hawking radiation. They will lose mass slowly, fading away until nothing remains but a thin sea of particles and radiation. When the last black hole disappears, the universe will be vast, dark, and nearly empty. A state known as the heat death or big freeze. In this distant future, no new energy will be created, no new structures will form. Space will stretch endlessly, and time will flow quietly onward. The universe will not end in fire or destruction, but in stillness, a perfect, infinite calm. And yet, some theories suggest this might not be the true end. Quantum physics hints that the vacuum of space may not be completely stable. Tiny fluctuations could one day trigger new regions of expansion, miniature Big Bangs giving birth to new universes, each with its own laws and constants. In that view, our universe might be just one bubble in an eternal multiverse, a single spark in an infinite chain of creation. Whether the cosmos fades, collapses, or begins again, one truth remains constant. Everything that exists today, from the smallest atom to the largest galaxy, came from the same beginning. The light that fills the sky, the matter that forms your body, the energy that keeps stars burning, all trace back to that first instant of expansion. The universe may grow cold one day, but its history, written in the atoms, the light, and the very fabric of space, will always remain. It tells the story of transformation, of energy becoming matter, of matter becoming life, and of life, looking back to understand where it came from. And perhaps that act of understanding is the universe's way of seeing itself, of becoming aware of its own beginning. When you look at the stars, you are not gazing at something separate. You are looking at your own origin, at the continuation of the same process that began nearly 14 billion years ago. The universe does not end. It changes form. It began as light, became matter, became life, and will one day return to silence. But even in that silence, there is beauty. The quiet rhythm of existence, still expanding, still moving, still eternal.